This slide deck provides a brief review of concepts from geometry and trigonometry that physicists routinely use. This deck is presented in two parts. In the first video, we describe the notion of flat space and the Pythagorean theorem. Physicists rely on the ability to describe the shapes of triangles in relation to circles, so we will use the second video to review trigonometry. Geometry handed down to us from the ancient Greeks rests on 5 postulates. We take it for granted that we know what it means to connect 2 points with a line segment. We take it for granted that we know what it means to extend a line segment indefinitely into a line. We take it for granted that we can draw a circle using 2 points, one point as a center and the other point touching the circle's circumference. We take it for granted that all right angles are equal. In a sense, we can say that the Greeks believed in equal rights. Intersect the blue and gold lines with third line in gray. If interior angles sum up to less than 2 right angles on one side of the gray line, then on that side of the gray line, the blue and gold lines inevitably intersect. This is to say, we take for granted the parallel postulate. How does Euclidean geometry speak to a physicist? One notion is the idea of working in so-called flat space. 2 ants walk away from each other, away from and toward the viewer. If these ants change course only once, with the ant in the distance making a right turn and the proximate ant turning left, they will never meet again. We contrast flat space with the surface of a globe. 2 ants moving apart northward and southward, turning at right angles, will eventually meet again. In this case, the parallel postulate appears to fail only in disguise. The 3 so-called lines defined by the paths of the ants are drawn as curves in a 3-dimensional space, which the viewer's intuition has probably automatically assumed is itself flat. There are other contexts, or geometries in which, for less mundane reasons, the parallel postulate does not hold. In these geometries, the collection of geographic locations that make up our world of exploration cannot be represented as a wrinkled or curved blanket sitting in a higher dimensional flat space. Discussion of this kind of geometry is beyond the scope of this slide deck. The Pythagorean theorem is another notion that physicists quickly think of when thinking of Euclidean geometry. A right triangle has sides of length A, B, and C, with C the length of the hypotenuse, the side that does not touch the right angle. Form 3 squares with sides A, B, and C. As interior decorators, we want to know how much tile to purchase to complete the flooring for the red room in comparison to the tile necessary to complete the yellow and green rooms. The wider a room is in the horizontal direction, the more columns of tiles it requires. And the taller the room is in the vertical direction, the more rows of tiles that must be laid down. The number of unit square tiles in each square room is A squared, B squared, and C squared. The number of tiles in the green room equals the sum of the numbers of tiles in the red and yellow rooms. We want to demonstrate that A squared plus B squared equals C squared. Arrange 4 copies of our right triangle so that their legs are flushly aligned. Each leg of length A is touching a leg of length B, which means that the vacant square or donut hole has sides of length A minus B. The area of the purple donut hole is therefore A minus B quantity squared. The area of a right triangle is half the product of the lengths of the 2 legs, so each blue triangle has area AB over 2. Green highlighting indicates the combined area of the 4 blue triangles and the 1 purple square donut hole. Together, this is A minus B quantity squared for the donut hole, plus 4 copies of AB over 2 for the triangles. Since this area is also the area of the green square with edge of length C, this sum is equal to C squared. Please pause the video and argue that the green shape must be a square. The term A minus B quantity squared can be expanded or FOILed into A squared minus 2AB plus B squared, and the 4AB over 2 turns into 2AB. Cancel the minus and plus 2ab, and we get a squared plus b squared equals c squared. The sum of the squares of the lengths of the legs of a right triangle equals the square of the length of the hypotenuse, as we sought to show. The length of the hypotenuse is the square root of the sum of the squares of the lengths of the legs. In this video, we illustrated a notion of flat space and walked through the Pythagorean theorem. In addition to these concepts, physicists regularly use relationships between the geometric properties of triangles and the geometric properties of circles that we will describe in the next video.